In this question, we have a highly charged metal ion which actually complexes with water and then kicks off a proton using water. So it's not that we need to worry about either of, the chloride ion within the salt cobalt chloride. Here, the signal that we have an important ion is that the size of the metal ion's charge is 3 or higher. And for that reason, it complexes with water. They even indicate this by saying the Ka value for cobalt 3 ion when complex with water is a certain number. When highly charged metal ions complex with water, it's always an acid dissociation. So we've got cobalt complexing with 6 waters, and it's not a huge deal if you get the formula of the compound wrong. What you do need to know is that it kicks off a proton because it acts like an acid. After kicking off one proton from one of the 6 water molecules, you're left with 5 intact waters and an O and an H from the 6th water molecule. And instead of a 3+ charge that we began with, you end up with a 2+ charge. All of that's kind of beside the point. It's just that we kick off a proton. They gave us that the initial concentration of the salt was 0.13, and we don't have any of the other species, so we shift to the right. And they actually give us the Ka value directly, which is really nice. It's 1.0 times 10 to the negative 5th, whereas in the previous problems we had to calculate the K value. Just like always, product concentrations all divided by reactant concentrations. We'll go ahead and make the mathematical assumption that the quantity 0.13 minus x is roughly equal to 0.13. When we solve for x, we get 0.00114, which is less than 5% of 0.13. To get pH, now that we have the value of x, and in our ICE table, x is the equilibrium concentration of hydrogen, we simply take negative log of that number. So negative log of 0.00114 works out to be 2.94. And that's our final answer.